Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the Maritime Structures course under Fire, Blast and Explosion offered by Swayam Prabha in the Department of Maritime Engineering at IIT Gandhinagar. Today we are going to take you around a numerical analysis for fire loads using a software by name PyroSim, thanks to Thunderhead Engineering Incorporation for giving us license to project the screenshots and the capabilities of this software for fire resistance modeling. So friends, I will take you step by step of doing this numerical modeling using screenshots obtained from the software. In the next lecture, Dr. Pratibha will take you around a live connectivity of this numerical modeling using this software, and she would explain every steps involved in the same manner as I am now explaining, but with the screenshots. PyroSim software offered by Thunderhead Engineering is one of the pioneer softwares to do fire resistant analysis and design. It has got lot of capabilities and it can also take you walkthrough of fire numerical models. It can also enable to program the results in such a manner can be useful as an output in other parallel application softwares. In most of the cases, as we learned from previous lectures, the flammability diagrams need lot of input from the fire models. So, if one can integrate the flammability diagram inputs from this output of fire system software, it could be very useful to handle fire mitigation processes as well as firefighting systems to make it more effective and more advanced, so that the devastation caused by fire can be controlled to a larger extent. Friends, as we understand that material loses its strength at high temperature, be it steel or be it concrete, does not matter. So, therefore, time versus temperature properties dependent of steel characteristics should become an input in the analysis. Pyrosim helps us to do that. First, Pyrosim helps us to create a fire load and then understand the consequence of fire first. It may not be useful for design directly using Eurocodes etc., but however, the output taken from fire model can become a very useful structural thermal coupled analysis in the next stage of fire resistant design, which you will see in detail in the next lecture number 20. So, now let us go through step by step of numerical modeling using Pyrosim. Why Pyrosim? Pyrosim is capable of importing the CAD models. If you have any model done in AutoCAD or Autodesk models, this can become input directly to Pyrosim. Pyrosim has an inbuilt SMB viewer and many other advanced features. As we proceed forward, I will tell you. Of course, I will not be able to highlight all the important parameters and capabilities of this software. I would urge that you should learn it on your own, or a very good support is also offered by Thunder Engineering. So, whenever you become a licensed user of the software, they are available on contact with you and you will be able to get their help directly by emails. So, I will try to touch upon important aspects and capabilities of this modeling, which is bare required to create a fire load in a given system and then desired output caused by the fire onto the system. Pyrosim also creates fire dynamic simulator record with a correct syntax. So, you will know all the steps involved in the dynamic simulator for fire, and the graphic user interface with fire dynamic simulator is a very important add-on and strength of this particular application, whereas FDS is used as an underlying simulator in the whole work. So, the model what we try to do in this specific application is a CFD based model, which helps us to model the complete dynamics of combustion, which is very required to obtain the exact effect or consequence of fire on a given structural member. It also involves text based Fortran with syntax, and of course, Pyrosim requires smoke view for visualizing the results obtained from Pyrosim. So, Pyrosim being a very powerful graphic user interface, it is linked with the pre and post process of fire dynamic simulator. Therefore, it is a real time software or application which helps to understand the dynamics of combustion and use fire as a real time input load on structures. If you look at the screen, how this application looks like, on the top you will see these appearing on the screen. They are basically the menu bar used in the system. You have a lot of toolbars which are useful in preparing the model, running the model, simulating fire, etc. So, we have toolbars just below the menu bar. On the left side, you have the navigation view. So, all available species for making fire model, for creating reactions, for creating surfaces, for creating inserting new devices and initiating controls are all available in this menu, what we call as a navigation view. And different kinds of modeling toolbar also available. You can drag and drop them on the left hand side of the screen. And to view the models, you have got 3D view, 2D view and record view. So, you have a model view tab at the bottom, and the black screen what you see here is actually the screen used for viewing the model. So, on the left down you will see the coordinate system. So, for the setting what I have currently used, xy becomes the plane which is vertical, which is on the screen, and z plane is normal to the screen. You can of course swap these screens as per our choice as we proceed with the model. So, friends, a very interesting user friendly application which can be easily learned, and you can get trained on this application if you want to really make the model very useful. Fire simulation process has got many steps involved in this application. The first step could be to prepare the geometry. So, we have to prepare a geometry where I want to apply the fire law. It can be a room, it can be a whole structure. You can also create this model in CAD and import it to this application. So, you need to have a geometry which contains all obstructions, openings, material definition in terms of its pure dimensions correctly modeled. Okay? Then only the effect of fire simulation can become realistic. So, we need a perfect geometry as a first step for this application. Once you prepare the geometry, then you have to identify and apply materials and surfaces to these elements, because unless the materials and surface are applied to these elements of this geometry, fire cannot recognize the combustible properties of these materials. We know fire load depends on the combustible property and characteristic of the material, and of course the mass of the material. So, you need to have a model, and the model should also have relevant materials and surfaces applied onto it. So, the second step could be assigning properties to the model. The third one or the third step could be creating the combustion model. So, we need to identify the fuel source and the amount of fuel. We should say ventilation control, fuel control fire, and we should also specify the reaction. So, this input becomes the third part of this modeling, where we call combustion reaction should be given as an input. Once it is done, before we run the model, we need to set the mesh and boundaries. So, now very interestingly friends, when we talk about meshing, if you are interested in working out the result output from a specific point, let us say A, the mesh should be included in that A. For example, if you have a mesh where you are choosing a point A here, which is on the border of the mesh, it may give you some error in the output. So, whatever point where you want to extract the output, mesh should completely cover that point in all respects. Preferably, the point where you want to extract should be the CG of the mesh. So, be very careful of choosing the mesh size and then point of interest where you want to extract the results. It should not lie on the boundary of the mesh. Okay, it gives you a different result. So, one need to specify the mesh, the boundary conditions and the simulation parameters, because we have learnt about the fire classification in the previous lectures. We know fire can become a vapor cloud, can become a pressurized flammable material. Therefore, the simulation parameters need to be set according to the fuel source and the reaction what you wanted to model in the given system. Once we have done the simulation part onto this, then the next step should be I want to generate the output. Friends, output is not as to generate from other graphical user softwares. In this specific application, output should also be generated only based upon any device you want. Any device, for example, smoke detector, temperature gradient of any point. So, you have to create a device on which or from which you will extract the output. You may say, sir, I already created a geometry. I want to find the temperature variation along the wall with its height and thickness. You can do, to do the measurement, you have to create a device. There are different devices available. As we proceed forward, I will tell you. These devices should be created and outputs can be only measured on those devices, not on the geometry or on the materials. Of course, the devices what you provide will be accounting for the characteristics of the material and the geometry automatically, but you cannot measure the output directly from the geometry or from the material without creating an output device. So, therefore, you need to create a basic data output. You may also fix certain firefighting systems such as sprinklers, smoke detectors, which are all readily available in the pull down menu in the application. You can also create your own custom based output devices if you want to so. Then the last step could be simulating the fire scenario, where I want to simulate with and without wind. I want to simulate them on a specific device. I want to simulate the results based on specific geometric condition. So, I can specify the simulation parameters for the fire scenario. For the same model, I can run different scenarios. For example, there can be successive fire. Fire 1 starts at 0 time, and explosion following fire can be starting around 30 minutes or 30 seconds after fire F1 scenario. I can input different scenarios and get the output for all scenarios independently or as a cumulative cascading effect. So, the application has got a lot of, let us say, modalities and flexibilities in modeling output. One need to understand them. So, I will explain them, few of them as we proceed forward. So, fire simulation process in the application essentially has 6 steps. Starting from the geometry, discussing the fire scenario, we need to follow these steps in the same order so that the model is now ready for extracting results for different scenarios as specified by the user. Having said this, now let us create a fire model. How do we do that? First, we create a model geometry, define fire scenario, then define the mesh to capture the results, then also insert devices, run the simulation and view the results in any device as per our choice. So, that is the step. You see here, create a geometry, assign properties and materials, define the combustion reaction, set the mesh size, simulate, provide devices to generate extract output and read the output. This is the step what we have installed. So, let us create this model and see how do we do it. As a result, first we understand, define the geometry. So, in this specific case, I am creating a simple room of a rectangular in size, and it is of course a solid model where I also have a height of the space. So, all these are to be walls, therefore, I need a thickness for these walls. Okay, I have given a thickness for these walls, and these walls also have height, and remember these walls will be on different planes. Okay. So, these walls will be handling or treated as obstructions for fire to spread. So, let us create a slab for the whole room. The slab will be on XY plane. It represents flat surfaces. You can also create walls for each room. There can be 4 walls, slab and a floor. So, it consists of 6 pieces of flat surfaces. Walls represent planar faces, maybe in XZ or YZ plane. If this is X axis, if this is Y axis, and this becomes my Z axis. So, walls will be in XZ plane, these 2 walls. These 2 walls can be in YZ plane. The slab will be of course in XY plane and so on. Remember friends, These elements have thickness and they are all planar surfaces. So, slabs represent horizontal flat surfaces, whereas walls represent upright vertical surfaces. You can also create a block inside the room, solid block, which can be identified a source of fire, maybe a table, a chair or a sofa or any specific equipment room, whatever may be the choice. We can also create a block model inside to create simple obstructions for flow of fire. We can also create opening for doors and windows, okay. We can create ventilators and so on. So, we can also create opening on the model for doors and windows and ventilators. So, I can define the geometry, which actually is the first step in this case. Okay. So, define the geometry. So, we have defined the geometry. So, to draw it comfortably, you can always create a mesh or a grid at the bottom. So, I can count the grids and I can give a proportional dimension for the room in plan as well as in elevation. So, the flat surface are created at two planes x, y, that is slab and the roof or slab and the floor. Then the walls can be your vertical surfaces, upright surfaces on xz plane or yz plane. You can also create openings for doors and windows and ventilators, etc. Okay. Now, the geometry is completed. We can also create an obstruction inside the room where I want to find out the effect of fire load on this specific obstruction. It can be a table, it can be a chair, it can be a machine room, it can be an electromechanical equipment, etc. For example, I want to find the effect of fire on a cable tray. I can mark a cable tray running from this wall to this wall at a specific height from the floor. When I insert a fire model, then I can also find what is the effect of that fire on this cable tray. So, I can always measure consequence of fire on any point of my choice, but for all of them I must have to first create a geometry. So, define the geometry first. Having said this, then I have to define fire. The moment I say geometry, it includes materials also, okay, materials and surfaces. I am creating a perfect geometry, material, surfaces, opening, all these are defined. Then I move on to defining fire. A fire can be defined in two ways. It can be defined in a chemical reaction, can be defined as a physical reaction, that is a surface. So, if you want to first define fire as a chemical reaction, identify the main parameter that governs the combustion. It can be methane gas, can be hydrocarbon gas, hydrocarbon fire, can be wood, it can be gasoline. You have to identify the main parameter which is going to initiate the chemical reaction. Then represent the chemical reaction. You can also use multiple reactions for the same building, okay, because depending upon the inventory available in a given model, you can also have multiple reactions. Interestingly friends, fire dynamic simulator has got an interesting reaction library. You do not have to worry about the reaction or chemical equation of this. You have to select the source, methane, butane, propane, wood, whatever may be the source. Fire dynamic simulator has a pull down menu reaction library. You can choose from that and pick up the points and reactions automatically inserted in the source. Once you set the reaction is set, then you have to say where is the reaction happening, that is the surface property of the reaction, physical. So, you must also say what are the physical characteristics of a solid or opening in a fire model, and you must also specify various types of surfaces for the given model. Okay. Having said this, let us slightly elaborate about surface and material. Material surface you apply on the model includes thermal properties also. There is a big library available within this application. You can always use the standard library. If you want to have your own material, you can also create your own library. Okay. You can also, so if you want to create your own library, there are three parameters required. One is the C value of every material, then the mass of that material, and of course, the coefficient of linear expansion, thermal expansion, etc. You must have all the chemical and mechanical properties of the new material. So, if you have these, you can always create your own library and read the material from that library and apply that material to any surface of a choice in a given model. So, material surface should be assigned, which must include thermal properties. You can also choose layered surface, because if you have a composite material, for example, I have a material which has got two different layers, one layer and another layer is a cover to this. So, we always do this insulation for walls, right. So, this is an insulator, both sides, maybe a gypsum board. So, I can say this is an insulator of a different material and this can be the wall of a different material. So, this can be a reinforced concrete wall and this can be a gypsum board. So, you can also create such composites materials here, okay, composites. Then you want to create opening, you can also create opening for windows, doors and vents in that element and cut this out and say this may window and so on. Okay. So, you can always do this kind of model detailing here with additional controls. There are menus available in the application, you can always do them. You can also do them in detail in the CAD model and import that model into this application, that is also possible. Now, let us come to surfaces. Surface is where I am going to define the fire reaction. Material is assigned to the geometry. Surface is assigned to the chemical reaction where the fire going to happen, the combustion reaction. So, it can be an adiabatic surface which represents no heat transfer, perfectly insulated boundary. You want to have a boundary like that. For example, let us say this is perfectly insulated, you can call this surface or assign this surface as adiabatic surface. So, it is perfectly insulated. You can also create something called inert surface. Inert surface does not require any material property, it just allows heat transfer, that is all. You can also create a burner surface which becomes a source of fire. Okay. Open command allow air exchange between the simulated space and the outer environment. For example, if I have a room, let us say I have created a wall, okay. Let us say there is a room and this is my flooring. So, this is one wall. Okay. I am defining a burner source here. It is a fire source for me. This is a fire source. Now, I want to see what is the effect of this fire which is sourced by some combustion reaction on this wall or inside this room. Let us say I want to see the effect of this inside this space, inside this space. Okay, there is a window here. Okay. So, in that case, if this wall is completely solid and inert, it will not allow. So, once I create this wall, can also use something called open command. I can also something called open command and make this particular wall which will allow the heat transfer. Okay. So, I can also use different commands, controls in the application where a complete wall like a screen allows heat to transfer inside. A complete wall can also remain completely, let us say, insulated, which will not allow the heat to transfer inside. In that case, heat will transfer through the surrounding part into this room. So, one can create these kind of variations in the model as depending upon the demand, one can do that. So, materials are assigned to the structural surface, and surface can be adiabatic surface which gives me insulated boundary, inert surface which allows heat transfer, burner surface indicating the definition of fire source, and you can also open close any specific obstruction by using this command called open. So, I can always create surfaces of my choice in the given application. Let us look at the screen of how to add a reaction, because I want to now initiate a chemical reaction, a combustion reaction for fire. I need to add a reaction. So, step number 1, go to the menu like model, say edit reactions. You can add the reaction from the library in step number 2, and once you select, then you apply, or let us say you can also choose something called gas phase reactions. It is available in the pull down menu from the library. In the gas phase reaction, you want to choose the wood oak reaction. So, it means the source of reaction of fire behaves like a wood oak. Okay, it burns like a wood oak. You can also create this source as propane, butane, any source you want. So, whatever source you select for the gas phase reaction, this will behave and react, or combustion reaction will be similar to the wood oak as you choose. So, once you choose that, it appears here as a current model, and you can export it to the list here. Okay. You want to modify them later, you can choose them and delete them as well. So, you can play around with the choices available. For example, you see octane, propane, nylon. Okay. There are many models available in the library. You can choose them as a reaction adding to the system. You can also have multiple reactions added to the system. So, not only one, okay, multiple reactions can be added. Once the reactions are added to the system, then we create and apply to a surface. Okay. So, what we do, go to the model, edit any chosen surface and call either new or old that surface as a fire surface, name it as a fire surface. Okay. The surface type can be a burner, there are many types available in the literature. In the application itself, pick up that and say OK. Once you say OK, then the burner appears there as a surface type. Then now you can set that surface to fire. So, while doing that, you can always choose this burner to be adiabatic, to be inert, and so on, as we said in the previous slide. Okay. So, then you can also specify, interestingly friends, the heat release rate per unit area, that is a flux for this source. Okay. Heat release rate per unit area. Okay. You can also fix that number as an input definer value. Okay. You can also choose either a single surface or multiple surfaces. Okay. So, while do that, you will be allowed to choose the geometry of the face, where you want to choose the surface. Either you choose the surface of the whole element what you have modeled, or you can choose the left and right coordinates of z, y and x depending upon the case of your obstruction, and you can choose that also. You need not have to create a solid model to make them as an obstruction. You can always choose the fire source obstruction directly by giving the surfaces here. Okay. So, choose a new surface, assign the type of reaction, choose the boundary at which this is going to act. Okay. So, create a surface and apply on the model. As I said, to understand the results, we need to have a mesh, because the model is now very big in size. I want to find refined values of these. So, this is going to simulate now panel by panel, mesh by mesh. Therefore, I need to specify the mesh. So, in the same model, you edit meshes and you can give mesh name and you can give the size of the mesh boundary. Remember friends, once you give the mesh boundary, it divides it into equal number of meshes equivalently, and the number of cells are indicated here. This cell should pass this number for the software application to work successfully. Okay. So, once this boundary and the mesh size you are given is okay, it tells me the mesh size is passed, and you will find this green tick here. If this green tick does not come here, then the model will not run. So, to do that, you got to modify the boundary size and so on. Okay. So, once you modify, the cell size is available displayed here, and the total number of cells in the mesh is also displayed. So, depending upon the capability of the model, capability of the system, because it needs lot of processing speed. So, depending upon that, there are some restrictions about the number of cells for mesh. If the number of cells are too high or the mesh is very dense, then the model may not run effectively. If the mesh is too large, the model will not be able to capture effectively the fire load or fire consequence. So, both ways there are contradictions. So, one has to be careful in choosing the mesh, and most importantly, you must get this mesh test passed, and there must be a green tick mark on the cell ratio. The cell ratio should approximately be 1. Okay. So, if it is not coming to be 1, you have got to change the mesh boundary accordingly, so that you bring these two things appearing on the screen as I show you. Hope you understood this. Okay. Next, I want to define the boundary conditions and simulation parameters. Now, the boundary condition for the whole analysis should be set in such a manner that the whole building or component of the building can be only viewed. The wider the boundary condition, the larger the boundary condition, it will take more time to process the fire dynamic simulation. So, one can also do segmental analysis. One can only look at a specific component consequence of fire. So, you can set a boundary according to that. So, you can choose the mesh what you have done in the previous step, and you can use the mesh size, you can alter the mesh, you can delete them, copy the mesh, scale them, rotate and mirror them, move this mesh, etc. for all these wherever you want to provide the model. Once you have set the mesh size and the boundary condition, now we go forward to find out the analysis output. So, to get the output, we need to run the analysis. So, analysis need to also set up simulation parameters. You choose simulation parameters from the pull down menu, then you can now check the simulation parameters as what you want to give, and you can also give for every parameter a title for the running model. So, you can choose the time, at what time you want to start and what time you want to end the simulation. Now, I have given here in the screen 60 seconds. So, one can also give as per your choice. Suppose you want to run the fire entry after, let us say, a specific lag time. So, you can always give the start time need not be 0, can be even 10 seconds, 1 minute. So, you can start or you can delay the fire process as you want for a given structural system. Okay. So, start time and end time is given for the time. Then also you can control, do not allow time step to exceed initial. So, you can also control these parameters, run the simulation effectively. Okay. And you can also update the wall mesh updates as how many steps you want, because you know TT curve varies the temperature and time. So, you need to also define the number of time steps you want to do the analysis. Okay. You can give a simulation title, you can also put the environment for this simulation. So, in this specific case, as you see on the screen, we have put the ambient temperature as 22 degrees Celsius. You can also set this, you can also set ambient pressure, you can also set ambient oxygen mask friction. So, all these input parameters can be given for the analysis as you see. So, once you set the boundary condition and the simulation parameters are assigned to the system, the next is to, once you give the boundary condition and simulation parameters, then we need to give the basic output data required. As I told you, the measurements cannot be directly taken from any model piece. Wherever you want to need the measurements output, you need to create a device. The general tools in finite dynamic simulator are for recording and generating output, for modeling sensors. You have to activate the real life scenarios there as through the devices. Whatever devices you have, sprinklers, smoke detectors, temperature detectors, humidity controllers, all those available in the library, you can use them as a real time activator scenarios and fix them on the model at any specific location, and outputs can be only generated through those devices. For example, in simple terms, if a model is complete, you have no devices given or defined in the model, you cannot extract any output. Fire simulation will run, but you cannot get any output. Outputs are always derived only through the devices. Now the question comes, what are different types of devices? You have gas phase device, which can be in the gaseous cell, that is in the space cell, which should be fixed at the center of the cell. You can have solid phase devices, which can be kept in a solid phase like a wall at the face of the wall. You can also keep smoke detectors to detect different parameters, which can also be kept on the surface of the mesh. So, different devices can be placed in different locations, okay, to get the heat. For example, I want to know what is the temperature variation within the thickness of the wall, okay, from here to here. Within the thickness, I want to find the temperature variation. I can find. So, I have to use something called solid phase device. If I want to find what is the temperature in smoke detector here on the surface, I must use this model or gas phase device. For example, I have an open space, I want to find the fire temperature variation at this open space here, I must use something called gas phase device. So, you have to choose appropriate type of the device to measure the output in the model. Friends, I reiterate again that if you do not assign any devices to the model, fire simulation will run, but you cannot read, extract any output. Outputs are always seen only from the devices. Okay. So, now defining devices. Let us say I take up gas phase device, which is going to measure the temperature variation at any point in space in the model. Okay. I can locate it in the z direction, I can orient in any place I want in x, y, z, I can locate this device in space, okay. Call them as gas phase device. I am going to use this device for measuring temperature. Okay. I can enable this set point of the device at any point I want. If you remember carefully in the previous slide, we said I want to start the model simulation from 0 degrees. So, if you have multiple devices and you want to set the enabling point of each one of them separately, you can specify that here. Okay. Now, if you want to measure the ceiling temperature, I can also go for a new device called solid phase device. The ceiling temperature is a solid model. I can measure just at the skin of the surface of the ceiling. I can go for a solid phase device. I can locate this at an height of 1.375 meters from the floor, ceiling height, or any point where I want. I can measure wall temperature using a solid device, and I also locate smoke detector at a specific location x, y, z and locate smoke detector. So, now in the black screen what you see in the modeling segment, we have located a device for measuring ceiling temperature, a solid phase device, a smoke detector and a gas phase device where I kept it in the opening. So, opening is a space, okay, it is an opening. So, in that opening I want to measure, I have created this opening for a doorway, I want to measure what is the temperature in the doorway. Why I am measuring this? Because If I have any heat source here, I would like to know at what time the temperature at this point will be reaching, say for example 200 degrees, because beyond that a firefighting man or any entry cannot be allowed in this. So, I want to know the temperature variation here with respect to time. So, I can do that by providing a gas phase device in space. So, 3 devices created, gas phase, solid phase and smoke detector are shown here. So, the locations of x, y, z coordinates of them can vary. You can locate wherever you want. You can also have multiple devices on the same floor, multiple type of devices on the same space. You can also delay their measurement by giving an enabling output, etc. Okay. So, defining devices. Friends, I reiterate, if you do not define the devices, you cannot take any output from this application. Having said this, so if you want to assign materials, we have already said that you can take these materials from the library. There are preloaded materials available. You can also use them. You can create your own custom material, but you need to give all inputs required as demanded by the application software. You can also customize your library for materials. Once material is assigned, then you can also give fire protection devices. For example, I want to put sprinklers at 2 different locations, so that once fire is activated and the temperature is, sprinkler bursts off and sprinkler starts pouring water and the temperature is controlled. I want to see that behavior. Okay. You can also locate control mechanisms like sprinklers, smoke detectors and alarms, mechanical ventilations and controls. You can locate these items also in a given space, and you can also see their behavior as temperature rises with time in the given simulation. So, if you want to look at the output only on a specific location, you can create a 2D slice. So, in a given system, you can create a slice at any plane you want, at any value you want, and measure only the temperature, and you can name these planar sizes and see. For example, let us say I have a wall, this is a floor, I have one more wall here. Okay, let me rub this part. Okay, I have one more wall here. Okay, this is the floor. This is the floor. Let us say I may draw a better one. Let us say this is my front wall. And I have one more wall here. Okay, I have one more wall here, and this is my ceiling. Okay, the perspective view, I think you will be able to see it. This is the floor. These are all walls. So, I have a window. For example, I have a door here. I have a door here. Okay, this is a door. I also have a window here. Okay. So, now if I want to find the effect of the fire on any specific location, what I do, I need not have to do the analysis for the entire object. I can always create a slice at any location measured from the wall and measured from the wall here. So, I have created a new slice, a 2D slice, and I can view the results only on this slice. For example, I want to know on this slice at this point what is my temperature variation. I can view it. So, I can create a 2D slice, place them anywhere I want and get the results. Okay. So, that is a very interesting dynamic part in this specific application. Also, I can define fire protection methods. As I already told you, I want to define sprinklers. I can create sprinklers, edit the surface where I want to keep the sprinklers. There are different types of surface available. I can also create an exhaust, a new surface, exhaust surface, create mechanical vents as exhaust openings, and also say that the exhaust will open automatically when the simulation reaches specific time, or the exhaust opens automatically when the detector activates because of the temperature reached at that location. So, I can do all these of control mechanisms which are commonly used for fire protection. Real scenario can be modeled in this application software. So, friends, you can look at the capabilities of this in a very flexible way, how this can be operated. Once I get this, I can run the simulation, run the fire dynamic simulator. I can run parallel files and store them and view the results. So, I can continue to find the results. I can plot time temperature curve. I can plot the effect of wind on fire. I can also do parametric studies by changing the whole scenario with different fuels, different boundary conditions, different fire protection devices. So, it has become a very interesting research problem without actually conducting solid experiments. With numerical simulation, you can always do wonders to find out the effect of different devices on a fire scenario. Then I can generate a detailed report with the data output available, and then based on the data and the report available, we can always redesign the system for fire safety. So, friends, interestingly, the resources are available for burning sources from SFPE handbook, or if you want to find the smoke control engineering handbook, you can also use ASHRAE. Fire dynamic simulator user guide is also available. In addition, PyroSim also has own user manual which is supported by Thunderhead Engineering when we become a licensed user. So, friends, in this lecture we learnt how to use an application software for fire simulation. So, it has got basically 6 steps. You have to first create the geometry, assign the materials, then try to identify the fire reaction, the combustion reaction, then prepare the mesh and the boundaries, then identify the devices where you want to measure the output, and insert control mechanisms, and then run the fire dynamic simulator and get the results. So, in the next lecture, friends, we will take a real example and try to run the results and show you how results can be extracted from this, and Dr. Pratibha will discuss about this. In the next lecture, we will help you to do hands-on experience. So, please use PyroSim as one of the effective tool for fire resistant design. There are many others available in the market. So, thanks for Thunderhead Engineering for advocating and permitting IIT Gandhinagar to use this as an academic demonstration for specific course. Thank you very much, and I hope they will extend support to people who intend to use this application for research and academic purposes. Thank you very much. Namaste.